You are given the daily price of a stock. You may buy on any day and sell on any day, as many times as you like, but you can hold at most one share at a time. For example, buy at $1 and sell at $5 for plus 4, then buy at $3 and sell at $6 for plus 3, 7 in total. The question is how to find that maximum systematically. The key observation: forget enumerating which day to buy and which to sell. At the end of each day you either hold a share or you do not. Only two states exist. Let us draw it as a state machine. The first state is cash. You hold no stock, and your profit is the money already banked. The second state is hold. You own one share. Buying moves you from cash to hold, and the profit drops by that day's price. Selling takes you from hold back to cash, adding that day's price. Two states and two edges. That is the entire structure of the problem. Unlimited transactions means we may bounce between these two states as often as we like. Each day we only ask, is it better to stay put or to follow an edge to the other state? The state machine needs one DP array per state. Here there are two, cash and hold. Their meaning: the maximum profit achievable at the end of day I while being in that state. Cash means you are flat. Hold means a share is tied up, and its cost has already been paid, so hold is usually negative. The final answer is always taken from cash. Ending while still holding is pointless. Translating the machine into equations is mechanical. Each state is reached either by staying in it since yesterday, or by following an incoming edge today. Cash has two sources. Yesterday was already cash and we do nothing, or yesterday was hold and we sell at today's price. Hold is symmetric. Keep holding since yesterday, or come from cash by buying at today's price, subtracting it from the profit. Advance both equations day by day, then read cash n-1 as the answer. Since each day depends only on the previous one, the space can be squeezed to O1. Time to fill the table. The top row is the daily price. The two rows below track the cash and hold states. Base case: staying flat on day 0 gives 0, buying on day 0 gives -7. On day 1, the price is only 1, so instead of carrying -7, we buy today. Hold improves from -7 to -1, while cash stays 0. On day 2, the price is 5. Sell, cash equals max 0, -1 plus 5 equals 4, the profit of the first trade. On day 3, the price drops back to 3, so we buy again carrying the 4 we earned. Hold equals max -1, 4 minus 3 equals 1. Note that hold is now positive. On day 4, the price is 6. Sell again. Cash equals max 4. 1 plus 6 equals 7. The two trades accumulate automatically. On the last day, the price is 4, so selling would be worse, and cash stays at 7. The answer is the final cash sell, 7. The first variant, exactly one transaction. The machine is no longer a cycle but a one-way chain. Buy once, sell once, done. The code differs by one line. When buying, we cannot write cash minus price, only negative price, because this is the first and only transaction, so no earlier profit can exist. This variant allows at most 2 transactions. The trick is to fold the transaction index into the state itself. Buy 1, sell 1, buy 2, sell 2. 2 states become 4. The 4 states form a chain, and the transitions are still stay or move. The answer is the sell 2 state, which naturally covers the case of doing only one trade. This variant raises the limit to k transactions. The 4 states we just built are the same pattern repeated twice, so repeating it k times gives 2k states. The time complexity becomes O(n)k. One shortcut: once k is at least half the number of days, the limit is vacuous, So fall back to the unlimited solution from the start of this video. The cooldown variant forbids buying on the day right after a sale. In machine terms, we simply add a state. Selling does not return to cash directly, but enters cooldown first. After 1 day, the cooldown state flows back to cash, where buying is allowed again. In the equations, the source of a buy simply changes from cash I-1 to cash I-2. The last variant charges a fee per transaction. This time, not a single state is added. It is still cash and hold bouncing back and forth. Only the weight of the sell edge changes. Cash equals max cash, hold plus price minus fee. Charging the fee once on each sale is exactly a cost attached to that edge. To summarize the state machine recipe, draw the states and edges. Give each state its own DP array and each edge one term in the recurrence, across all 6 stock problems. Limited transactions, cooldown, or fees. Only the number of states or the weight of an edge changes. The framework stays identical.